Alrighty, hello everyone. Happy Monday or Tuesday, whichever day you have geometry. Thank you for your patience with the various teachers being out due to the COVID precautions. I'm going to take you through the geometry notes for Monday the 25th and Tuesday the 26th. We're going to be looking at some polygon basics and some angle measurements. I'll try my best to stick with the technical terminology. Thankfully, Mrs. Rose Johnson tends to help me out with that. If you do have any questions, though, feel free to email Mrs. Rose Johnson. You'll be able to contact her, and hopefully she'll be back later this week. Or you can come see me over in C106 until she gets back, and I'll help you out there. Okay. Anyway, you guys have probably heard the term polygon. You've been hearing it for years, and the basic definition is you would say, okay, a polygon is a shape. Well, technically, yes, it's a shape, but like with everything else in geometry, you have to be a little more specific. You gotta use some criteria in terms of what makes a shape a polygon and what disqualifies it from being a polygon. Okay, so let's look at the three basic criteria here. Thankfully, we've got an example and a non-example to go with it. So the first thing a polygon has to have is it has to be a closed shape. Notice there's no openings or gaps. If you have any openings at all, you say, nope, that's not a polygon. It's just some broken shape that qualifies as something else. So it has to be a closed shape. Second criteria, it cannot have any curved edges, whether it's a triangle, a pentagon, whatever. It has to be made up of nice flat sides. If there's even one curved edge or side, that's going to be enough to disqualify it from being a polynomial. Feel free to pause this as needed if we're going too fast. This video will be posted on Google Classroom as well if you need to go back and look at it. The third criteria, this one's probably the more complicated of the three. But they say, it can't have any more than two edges at a vertex here. So if you use the little star diagram, let me move it up so you can see it. Think of these two flat sides coming together and they meet at a vertex or a corner, if you want to say it that way there. But there can't be more than two edges meeting to make that vertex. Whereas over here, notice that this shape kind of crisscrosses over itself multiple times. So that's definitely not going to count as a polygon. Polygons tend to have to be, open in the middle of it. You can't have these crisscrossing trails. Okay, so that'll come in handy when they ask us to classify polygons versus non-polygons. Did I say polynomial a minute ago? I meant to say polygon. Sorry, got algebra on the brain. But yeah, we're dealing with polygons. We're not going to see any polynomials in this chapter. Okay, so let's say you've decided a shape is a polygon. Well, if it is a polygon, they're going to ask you to go a little bit deeper down the rabbit hole to classify it further. So if it was not a polygon, you would just say, no, it's not a polygon, and then you'd move on. But if it is a polygon, then we've got some further branches that we can classify it with. These two terms, concave and convex, the more you see them and the more you use them, the more comfortable you're going to be with what they mean. Practice makes perfect, just like anything. Here's the way I think of it, you guys. When I see the word concave, I think of it as meaning, all right, a section of the shape has been caved in or pushed in, so to speak. Notice right here, we kind of got this little indentation here. Instead of it being pushed out, somebody's like pressing it inward there. So any shape that has that sort of inward vertex, that's going to be concave. Notice that would also qualify to the star. Up here, you got a lot of instances where it looks like someone took the shape and pushed it inward. Whereas convex, that just means there's no caved in sections. It's just a nice, strong shape that has all of its edges out around the outer perimeter, so to speak, if that makes any sense. So even if you can only get the handle on what one of them is, that's going to mean, okay, it's this one, and therefore it's not this one. All righty, awesome. Going down that rabbit hole even further. So you've decided it's a polygon. You've decided whether it's concave or convex. Well, here's some other criteria that might come up. is that they're going to ask you, is the polygon regular or not? So let me start with the non-regular. You probably remember some of these terms from last semester. Maybe it's come up a little bit this semester too. Equiangular, that means every angle in the polygon has the same measure, or congruent angles. And then, or it could be equilateral, meaning all the sides are congruent. So if it's just one of those two things, it's not going to be enough to be regular. Whereas if it's regular, like over here, just like you think, regular just means, you know, kind of basic, kind of the perfect version of it. An example of a regular polygon would be, you know, something simple like a square. All the sides have the same length and all the angles have the same measure. And it's not just squares. You could have a pentagon where all 5 sides have the same length and all 5 angles have the same measure. So it needs to meet both criteria. It has to be both equilateral and equiangular in order to qualify as regular. It's kind of an exclusive club. That's why there's so many parameters you have to hit in order to make that fit. So it's pretty easy to recognize a regular polygon when you see it. Whereas if it looks a little imperfect, so to speak, then it's going to be non-regular. Okay, let's keep on cruising and see what else is going on. Okay, like I said, this video and this filled-in note sheet, we'll try to make sure we post it on Google Classroom for you. I don't want to spend a lot of time on this, but something you might want to familiarize yourself with as time goes on. These are just the names of different polygons depending on how many sides they have. You might already know quite a few of these already. You know that 3 sides means it's a triangle, 4 sides means it's a quadrilateral, 5 is a pentagon, and 6 is a hexagon. Who would have thunk it there? Here's where I get a little rusty on having the names memorized. I've gotten a little better over time, but you know, anything above 6, you might want to refresh just so you have them in your memory bank. 7, heptagon. You probably know 8 as an octagon. 9, it kind of sounds like it has the word 9 in it, a nonagon. 10, we got a decagon. Think a decade has 10 years in it, so decagon has 10 sides. But then what tends to happen is you'll notice we don't necessarily have a fancy name for an 11-sided polygon. There's probably a fancy name for it somewhere, but like I said, I forget off the top of my head. The last one that you might actually see a name for is a 12-sided figure. I don't really have a cool way to help you remember this, but you know, maybe think of it this way. It's got decagon in it, but it's got 2 extra letters, so 10 sides plus 2 more gives you 12-sided or a dodecagon. Here's where it gets a little easier though, because once you get beyond 12 sides, we just start labeling them with the number. So 13 sides is a 13gon, 14 sides is a 14gon, so on and so forth. So like we said, just try to familiarize yourself with these different names, because you might not necessarily have this list at your disposal all the time. Okay, let's see what's shaking in these examples now. We've laid the groundwork. Let's see what's actually going to be happening here. Okay, you'll probably see the homework assignment start off like this, where they ask you, is the figure a polygon? And it's not just a yes or no, because as you can see, the directions might want you to go a little further depending on what your answer is. Okay, is the figure a polygon? So let's take a look at it here. Remember those 3 criteria. First criteria was it has to be a closed shape. I don't see any openings or gaps in this one, so that's good. Second, a polygon cannot have any curved edges. Looks like we got just nice flat sides on this one. And then finally, the criteria was you can't have more than 2 sides meeting in a vertex. So even if you look at any of the corners, whether it's here, looks like that's made by 2 vertices coming together. If you look at this corner, it looks like it's only made up of 2. So it doesn't look like anything too strange is going on here. So it looks like our answer is going to be a yes for this one. Meaning, yes, it's a polygon. So we get to skip that part. But don't forget this little bit of criteria. If it is a yes, they want us to classify it by the number of sides. If we were to just count 1, 2, 3, 4, 5, 6, 7, I believe. So it's not wrong if you just put 7 sides, but we really want to encourage you to start using the vocab. And we set up above that if it has 7 sides, it's known as a heptagon. All righty, cool. Moving right along, we might have seen a shape similar to this on the front. It may be a little hard to see just because the shape is a little small, but when it asks us, you know, is it a polygon or not? Well, it doesn't have any gaps in it. Looks like we don't have problems at the vertex, but what we do have is this. Again, I know it might be a little hard to see in this particular diagram, but that's technically not a corner. That's a little curved section right there. So if you remember from the front, any curved sections or sides, that's going to disqualify it from being a polynomial. So we're going to put no, and then it said, if no, put why not. So something along the lines of no, because there's a curve. Just like anything in geometry, you know, we can't just put yes or no. We have to justify why we're doing that. Okay. Awesome. Now they're getting a little more specific of what they're asking. Here, they're telling you that all these are polygons. What they're asking this time is they're saying, okay, is the polygon regular? If you remember from a few minutes ago, we said that in order to be regular, a polygon has to have 2 bits of criteria. It has to have all of its sides equal length or equilateral. Looks like here we've got all 3 sides congruent, but then it also has to be it also has to be equiangular, meaning all the angles are the same. This is something that we came across in the previous chapter, where even though they don't have the angles marked for you, the rule was that if a triangle is equilateral, then it tends to end up equiangular as well. So this one is a yes. It only said to explain if it was a no, but if you wanted to add on to this, we could say yes, because it's equilateral and it's equiangular. Okay, over here, oh boy, we're in trouble already. Once again, you don't know anything about the angles, but that's okay. Just take a look at the sides. These 2 are equal in length, and these 2 are equal in length, but we don't have all 4 of them being equal in length. So remember, it has to be both equilateral and equiangular in order to classify as regular. This one is not equilateral. It's got 2 pairs of different side lengths. So this one's going to be a no. And depending on what you want to say, you could say because it's not equilateral. Or you could say something like, you know, only a couple of the sides are congruent to each other, etc. But as long as you're getting the point across using the definitions and criteria, you should be fine. All righty, last but not least of those ones, this one's going to be the trickiest of the bunch. Just a little spoiler alert. Okay, we only know stuff about 2 of the angles. So sure, we can say 2 of the angles are congruent. It doesn't indicate or say that all the other angles are 90-degree angles. We don't usually want to go by what a shape looks like, but on occasion we can look at it and say, okay, well, if these 2 angles are 90 degrees, there's no way that some of these other ones are going to be exactly 90 degrees. So already we've got a red flag. Already we could possibly argue that this is not equiangular, so it's not going to meet that regular criterion. We also don't know anything about the sides, so we can't claim that it's equilateral. Looks like neither one of those criteria are going to work. But the cherry on top one then that's easy to lose sight of is previously we said that there's another little piece we have to examine here. So in other words here, in order for a polygon to meet that regular criteria, it has to fall under that convex criteria as well. And if you'll notice, we got one of these arrow shapes. It says, okay, it looks like some of the sides are being caved in. So that as well, since it's a concave shape, would be enough to disqualify it from being a regular polygon. So there's lots of different things you could put for that. You could say, no, it's not a polygon, or excuse me, no, it's not a regular polygon because it's concave. It would have to be convex in order to even have a chance of being known as regular. So you could say no because it's concave, but you could also say no because it's not equilateral, or no because it's not equiangular. It has to have all those traits in order to meet that regular status. Yeah, some of them are a little trickier than others, but you guys will get the hang of it. Moving right along, here's where we're going to do a little bit more number crunching. We've done the classifying, we've done the definitions, but now we're going to get into some actual numbers. Okay. What they're going to start asking you is they're going to say, okay, here's a polygon. Try to find the sum of the interior angles. In other words, you're trying to figure out what all the angles inside add up to. You've seen enough triangles to know that the angles inside a triangle, the three of them, they always add up to a total of 180 degrees. So that really shouldn't surprise you because you've seen that before. What happens when you get to beyond three sides, or shapes with more than three sides, is it comes down to how many triangles you can break the shape up into. So that's what this little dotted line is doing. It's cutting this four-sided figure, or this quadrilateral, into two separate triangles. And notice what the formula does over here. It's saying, okay, we've got that 180 degrees that's contained within every triangle, and we're multiplying it by how many triangles the shape can be split up into. In other words, it's like, okay, this area or this triangle had a total of 180 degrees, and this triangle as well had a total of 180 degrees. Together, they give you that total of 360. That pattern continues as you go to bigger shapes. All right, here we got a pentagon. You split that up into three triangles. That's why we got the 3 here. And not that you have to write this every time. I'm just showing you where it all comes from. So that's why you're doing 3 times 180 degrees. So any pentagon is going to have an interior angle sum of 540 degrees. It does get a little more complicated as you go. Notice how they jump from 5 to 8. You might have to play around with this type of shape a little bit. Even if you divided it up slightly differently than how this picture does it, you should find that it'll take 6 triangles to sort of fill that space. So it's the number of triangles you're able to fill it with times 180. And notice the larger the shape gets, the larger the sum of the interior angles gets. Okay. Well, let's say you're sitting there going, okay, well, I don't know if I'm going to really remember to cut it up into triangles. What if I cut it up into more triangles than I need to? Well, this is something that's going to be beneficial to you because there is a formula for those of you that just prefer to rely on a formula and not go about it the exploratory way. Okay. Let's fill in the general version. So up here we said, okay, we had sides of 5, sides of 8, but now let's say we have sides represented by n minus 2. Now you're probably wondering, okay, where the heck did that n minus 2 come from? Well, take a look at some of the formulas we came up with up here. An octagon has 8 sides. So 8 minus 2 would give you 6. That's why we got a 6 hanging out in our formula. A pentagon had 5 sides. 5 minus 2 is 3. That's why we have a 3 in the formula. Some of you might see where this is going. But basically what happens is n is however many sides the shape has, and here's how you represent it symbolically here. You've got S with a little I on it. That's sum of the interior angles. And the formula goes as follows. You take 180 degrees, just like we did in these previous calculations, and that always gets multiplied by n minus 2, again, with n being the number of sides the shape originally had. If you want to fill that in, that would definitely be encouraged. So n is number of sides. And another way of thinking of it here is that expression n minus 2, that tells you the number of triangles you can carve the original shape up into. All righty, awesome. So that's typically what you're going to rely on. Sometimes they don't even give you the shape. But if they did, you could, carve it up into triangles. Or if they just give it to you in words, that might be where the formula comes into play, which is what we're going to look at next. Okay, we're going to put that to some use. I'm going to calculate the sum of the interior angles of a decagon. See if you remember without looking. How many sides does a decagon have? If you said 10, you are correct. What did you win by being right? Absolutely nothing. Sorry, let's continue. So anywho, if a decagon has 10 sides, we're going to take 10, and we're going to plug it in for n in this formula right here. We want to try to be as consistent as possible with using the formula. The only way you get used to it is by using it. All righty. So I'm going to plug 10 in for n. Remember, I'm just using this formula up here, but I'm putting the number of sides in for n. Now you're just gently going to crunch that out. Hopefully we agree 10 minus 2 is 8. Then if you need a calculator, go right ahead. 180 times 8 is going to give you 1,440 degrees. Don't forget your degree symbol because you are measuring an angle sum. Alrighty, awesome. Fun times. It'd be nice if they were just going to be that calculation over and over again. They tend to like to mix it up a little bit, which might be what they're doing in this next one. I don't know for sure. Let's just go have a gander. Okay, up there. They're switching it up already. It was only a matter of time. Now they're saying they want us to classify the polygon, which means we might have to do a little more digging. I want us to classify it by the number of sides, meaning here they don't tell us if it's a hexagon or whatever. They want us to figure that out. But they do give us the sum of the interior angles. All right, what I'm going to do is I'm going to jot down that formula that we just used up above. Okay, we're still using this formula. Here's the difference. We don't know the n value. That's what they want us to find. However, we do know the sum of the interior angles, which means we're going to take that 2340 and we're going to plug it in right here. Everything else, though, that's going to stay exactly how it is. Basically, your game plan is to solve this equation for n. And there's a few different ways of doing it. If you're working a little ahead of where I am right now, your first instinct might be to distribute 180 through the parentheses. That's totally fine if you want to do that. There's a slightly different way I might go about it here. In other words, you guys know that this means 180 times all that. So what you can do as well is you can divide both sides by 180, and that'll actually save you from having to distribute. Use a calculator if you need to. This divided by 180 will give you exactly 13. Okay, yeah, that's a little bit nicer than what you would have gotten if you distributed, because now you're going to solve this the same way you've done for years, just by doing some inverse operations, and you get n equals 15. Okay, Here's where we want to make sure we use the technical lingo. That goes for me too. Yes, you found that n equals 15. In other words, this shape has 15 sides. We just have to put a name to it. And if you remember on that previous sheet, that once we get to 13 sides and beyond, we just label the shape using the number. So we want to say that this shape is a 15-gon. Awesome. Like we said, that's just one way of doing it. Here's just the alternate way. I might not keep it up there very long, but certainly check it if you did it this way. This is how it would come about if you chose to distribute the 180 degrees. You get those pieces, you would add 360 to both sides. Here you would divide by 180, and notice you still get that n equals 15. So just make sure, whichever way you do it, hopefully you're getting 15 for that one, and make sure you label it as a 15-gon. That classification is very important, and we want to practice using the terms. Okay, let's see what else is brewing. More number crunching, I believe. Whatever it is, we will face it together. Okay, let's start with I don't want to say a basic thing, because that's going to imply that it's totally easy and obvious, which it's not always the case. But let me just point out what some of this stuff stands for. It does say off to the side, but the little I means interior and the little E means exterior. So what they're getting at is if you take any polygon and you've got the interior and the exterior angle, the ones that are kind of side by side like that, notice that they make up a full straight line. So one characteristic to take into account is if you add the interior angle with its exterior angle, that's going to equal 180 degrees, just like a flat straight line is. Okay, and we're going to see that a little more depending on what they're asking us for. They give you a little more detail here. We're going to fill in some of the pieces as we go. So if we look at this lovely little shape here, there's not a whole lot to fill in. Just notice that any angle you look at on this shape, whether it's interior or exterior, it does pair up with the opposite to form 180 degrees. So notice you've got 90 degrees and 90 degrees gives you 180. 140 and 40 gives you 180. 130 and 50. And then you got pairs of 90s again. So no matter where you look, the interior angle and its corresponding exterior angle add up to 180 degrees. There. What they also want you to take away from that is if you go around the outside, look at what all the measures of the exterior angles are. You've got 90, 90, 90, and then you've got 50 and 40. 90 plus 90 plus 90, that gives you 270. And then 40 and 50 gives you another 90. So together, those exterior angles add up to a total of 360 degrees. I might have jumped the gun a little bit on filling that in, but oh well. What you're going to see is no matter how many sides a polygon has, the sum of its exterior angles always add up to 360 degrees. Let's look at a few other examples just to drive the point home. Okay, we've got a shape that's only got 4 sides instead of 5 like the last one. So if you do 90 plus 90 plus 90 plus 90, guess what you're going to get? Yep, 360 again. Same thing even if it's a triangle. You've got 90 plus 120 plus 150. All 3 of those exterior angles, again, add up to a total of 360. In other words, depending on what type of polygon you have, the sum of its interior angles can be a specific value, but the sum of a polygon's exterior angles are always going to be 360. Or if you want to think of it in formula form, think of it this way. At 360 degrees, for regular ones anyway. Remember, regular polygons, that's when all the sides are equal, all the angles are equal. So if it's a regular polygon, you can just take how many exterior angles there are and multiply it by the number of sides. For instance, it doesn't so much work for this one because this one's not a regular polygon, but this one it certainly does. You got a nice square. All four of the angles are equal in value. All four of the sides are equal in value. So you got 1, 2, 3, 4 exterior angles, each measuring 90 degrees. So it's like you're taking 90 degrees, multiplying it by how many there are. 90 times 4 gives you 360. This may seem like a lot of detail being thrown at you, but just know, like everything in geometry, the more you use it, the more comfortable you're going to get with it. And, you'll certainly be able to look back on this just to find the pieces that you need. All righty, we're getting there. Let's do some more examples using that awesome stuff we just looked at. Here's where I want to make absolutely sure I know what they're asking us. They want us to solve for x. Sometimes they want you to plug x back in, find something else. Thankfully, they're going to keep these just nice and simple. Say solve for x and go from there. Okay, the first question is this. Have they given you interior angles or exterior angles? And hopefully your answer to that would be, all right, they've given me exterior angles. It looks like it's not a regular polygon because, we got kind of a lopsided shape. And notice that those exterior angles, they're all slightly different values. So it's not going to be a regular one. Instead, here's how we want to think of it. Back up here, we said any polygon has its exterior angles giving us a sum of 360 degrees, which means if we know all exterior angles here, we're going to take all four of these labels that are on the outside. We've got the 96, we've got the 88, we've got the 80, we've got the X, and we got the 70. We're going to add those all together because together those exterior angles need to have a sum of 360. In other words, you could set it up kind of like this. It doesn't matter which one you start with. I'm just going to start with the 96 and go around that way. So we're going to do 96 plus 88 plus 80 plus X. Make sure you can actually see it. And then plus 70. Don't forget about the 70. All together, that's going to give us a sum of 360, regardless of how many sides the shape has. Okay. Now you got your setup. From here, it's just a matter of putting it all together. Stuff you guys have been doing for years. You can combine all these non-X terms. Feel free to use a calculator if you need to, but we're going to get 334. We still got it equal to 360 over there. Blah, blah, blah. Use your inverse operations. Go ahead and subtract it from there. And that's going to give you an X value of 26. Uh-oh, I forgot my units. It's an angle, so I need to make sure I say that it's 26 degrees. I know on some of the homework assignments, especially when you do them on the Google Forms, the question might just ask you to type in the number without the degree symbol. That's just something that makes it easier for us to grade. So if you're doing it on paper, especially on a test or whatnot, just make sure you're putting the degree symbol when you're actually measuring an angle. Okay. So that's the upside to the exterior angles, because exterior angles always combine to equal a total of 360. Whereas where things might get a little more complicated is when they give you the interior angles. This is sort of going to be a two-step problem. Here's why. The interior angle sum, that changes depending on how many sides the shape actually has. Hence, before we try setting up an equation, we have to figure out what the angle sum of all these interior angles actually is, which means we're going to bring back a little pal that we used before. We're going to use that sum of the interior angles formula, where we did 180 degrees times n minus 2. If you quickly count, 1, 2, 3, 4, 5. So this shape has got 5 sides, which means I'm going to do 180 times 5 minus 2. You could punch that all into a calculator, but I might recommend going a little more gradual. 180 times 3 gives you 540 degrees. Now, that's not our answer yet. That's just telling us what all of these interior angles have to add up to. So that means we're going to take the 540 and we're going to use that in our equation. I'll do it here in a second so you know what I mean. But once again, we're going to take all these numbers or variables, whatever they've given us, we're going to combine them all in an equation, but we're going to set them equal to 540. In other words, we're going to get a little something like this. It doesn't matter what order they go in as long as all 5 of them are accounted for. So we've got 91 plus 140 plus 82 plus 137 plus x equals that 540 that we got a minute ago. I might pick up the pace slightly because, you know, once again, you're going to combine your like terms. All 4 of those other numbers give us a 450. And then, of course, you would subtract 450 from both sides to get an x value of 90 degrees. The setup can be the trickiest part, but I'm willing to bet once you guys have this equation locked in, it's going to be a piece of cake for you. The other thing I want to really steer you away from, we said that in geometry, you can't just go by what the shape looks like. Some students might argue that when they look at that, you know, they might think, oh, you know what, that looks like about 90 degrees, so I'm just going to guess that as my answer. You can't guarantee that it's exactly 90, because for all we know, that could be 88 degrees, it could be 95 degrees. So that's why you really have to go with what you're given. You can't typically go by what it looks like. You don't want to judge people based on their looks, and you don't want to do that to polygons either. Okay, now to bring it to a close, we got sort of a general scenario, but we like to go a little bit deeper sometimes. We could do number crunching all day. We don't want to lose track of the bigger ideas. Okay, little written portion. We got a student that claims the sum of the measures of the exterior angles of an octagon is greater than the sum of the measures of the exterior angles of a hexagon. Oh boy, that is a lot to digest. So what I'm going to do is I'm really going to hammer home what they were talking about. Okay, 2 different shapes. Octagon having 8 sides, hexagon having 6 sides. The student is justifying this claim by saying that an octagon has 2 more sides than a hexagon. Okay, so here's what it comes down to. We were using different formulas and different rules throughout this lesson. And notice that one of the keywords is exterior, meaning exterior angles. While yes, it's true that the sum of the interior angles changes based on how many sides it has, that's why we have to use this formula, we said earlier that no matter what shape you are given, the sum of the exterior angles always add up to a certain amount. I don't know if anybody remembers it, but if not, it's right up here. Sum of the exterior angles is always 360 degrees. So when they say describe the error that the student is making, you can phrase this different ways here. I don't think you guys need to watch me write it out, so we'll just go to the source. Something like this here. Mrs. Rose Johnson has much better handwriting than I do, so we might as well put up what she's got here. Okay, so depending on how you want to put it, feel free to rephrase it, but Mrs. Rose Johnson sums it up nicely here. She mentioned that, you know, okay, the student is thinking that the exterior angle sum depends on the number of sides, but we just saw a minute ago that that's not true. It's the sum of the interior angles that's dependent on the number of sides. This student was incorrect because sum of the exterior angles is always 360, regardless of how many sides it actually has. Lots of different things you can put for that as long as it justifies what went wrong. Okay. Adding on to that, it might be kind of paraphrasing what I just said there, but describing when the student would be correct. That was the idea that the student would be correct if he or she was calculating the sum of the interior angles. You got a hexagon with 6 sides, an octagon of 8 sides, then yes, the octagon would have a greater interior angle sum than the hexagon, but when it comes to the sum of exterior angles, everything is equal and you got a level playing field. Okay, thank you for your time, everybody. You'll basically have 2 assignments in one. It's going to cover all that good stuff we just talked about. You'll also see a grade point average calculation sheet in your assignments as well. For those of you that are going to be attending in person this Wednesday, we are going to look at that and talk about it together. If you are a student who is not going to be attending on Wednesday, please watch the video posted on Google Classroom and fill out the Google form that goes along with it. Remember, your Wednesday assignment, which in this case is the GPA lesson, that's also going to count towards attendance for Wednesday. Feel free to contact me, Mr. Murphy, and C106 if you have any questions over the next few days. Or, of course, email your teacher, Mrs. Rose Johnson. Even though she's out, she is totally willing and able to respond to you or give you any assistance or clear anything up for you until she gets back. All right. Thank you, everybody. Enjoy the rest of your day. Peace out.